This is the infinite plane problem. We have some electric charge distributed uniformly over the surface of a infinite plane, a thin infinite plane, and we would like to find the electric field produced by the plane at a point at a distance c. So in this picture, this square-like thing somehow represents the infinite plane. Unfortunately, there is no better way of drawing an infinite plane on a two-dimensional screen like that. Somehow I have to show boundaries, but of course these boundaries should be at infinity. So usually I show the picture like that, but I don't think that this is a reasonable picture. In any case, there are no boundaries basically in a really infinite plane. But without boundaries, I cannot draw those things. As a result, I'm just going to draw a shape like that. And then, most of the time, this is what I'm going to do. So you have to look at the text to see if it is really infinite or not. Another point of view might be something like this. So this might be a rectangular plane, perhaps, with some certain dimensions. So let's say that these are the dimensions, dd prime, let's say. In that case, we might be assuming that the size of the plane is much larger than the other dimensions, the length scales that appear in the problem. So here, for example, I'm looking at a point which is at a distance z from the plane. This is a perpendicular distance, basically. So in that case, we have to assume that the size of the plane is much larger than z. So as a result, essentially, I can assume that this is infinity. So in most of the applications, this is the situation that we have. So we have finite planes. Usually these are metallic slabs. The shape is irrelevant. Somehow the size of these metallic slabs is much larger than the typical distances from the plane. So as a result, in that case, we can treat them as infinite. In any case, so what's the electric field produced by this plane at this point, at a point in here, where z is the distance of the point from the plane? Okay, so because of the difficulty in drawing such kind of pictures, sometimes I'm going to draw them on a cross section, basically. So you can think of it like that. So I will take this cross section, for example. Think of it like that, right? In any case, that means I'm just looking at the side view. So from that side view, the infinite plane actually looks like a single line. That's actually better. So it's a thin line. So my point is in here, and z is the distance of the point from the plane. And I'm looking for the value of the electric field at that point. Okay. So that's the question. Sometimes I'm going to show the problem like that. So when I use these kind of symbols, sigma is always the surface charge density, then you can actually understand that this is really a plane, not a line. So there is actually part of the plane which is pointing, which is actually moving, or yeah, it's basically there's also a part of the plane which is perpendicular to the screen. But this is the part that we don't see. In any case, because of the symmetry, the electric field is either outward or inward. So we can actually use the same kind of a language. So we can choose the z-axis as an axis which is perpendicular to the plane, and so therefore this would imply that the electric field has a z component which can be positive or negative, but it has no x or y components. And x and y directions are basically parallel to the plane. Okay, so how do we solve this problem? Well, since the plane is infinite, we don't have to think of it in like a square or a rectangle. We can think of it as a disk. So this is the approach that we are going to take. So suppose we have a disk with radius r, right? And suppose that my point is at a distance z from the center of the disk. So I know the expression of the electric field produced by that disk in here. So let me, sorry about that. This is the electric field. I'm going to write down an expression for this in a moment. Let me correct this. The radiuses are. So what I want to do is basically just write down the electric field and then take the limit where the radius of the disk goes to infinity, and then compute the electric field there. So we have computed this expression for a disk with a given total charge. Unfortunately, for an infinite plane, the total charge can only be infinite. So as a result, I cannot specify the total charge in here. So in these kind of situations, I have to specify the surface charge density, right? This is also done in the original problem. So as a result, I'm going to write down the expression of the electric field in here in terms of sigma. So let's just remember this expression, sigma over 2 epsilon 0, and then 1 minus the absolute value of c divided by the square root of r squared plus e squared, multiplied with the signum z. Okay, so basically we need to take the limit where the radius of the disk goes to infinity. But since the radius of the disk only appears in here, when this thing goes to infinity, so this whole expression becomes goes to 0. And so as a result, we basically have this expression in here. So let me write it down like that. So this is equal to sigma over 2 epsilon 0 times signum z. So that's the expression that we want. So this might be a little bit confusing at first. So as a result, I'm going to draw it like this. First of all, let me plot this as a function of z, just as I have done before for the case of disks and annular disks. So I'm going to use a blue color. So you can see that apart from the signum, the expression doesn't depend on z, so therefore it's just constant. And it has the value of sigma divided by 2 epsilon 0. There is a discontinuity in here, so therefore on the opposite side of the plane with a negative z component, the electric field has a z component which is minus sigma divided by 2 epsilon 0. So therefore this is also constant like that. And there's a jump discontinuity in here. All right, so that's basically the feature in here. What does it say about the, let me also do this for the physical picture. So if my plane is in here, so that's the plane now, with surface charge density sigma, in that case what I'm saying is that the electric field on the right side of the plane is uniform, and it basically has a value of magnitude of sigma divided by 2 epsilon 0 along this direction in the direction in which you are moving away from the plane. And on that side, the electric field also is has a magnitude of sigma divided by 2 epsilon 0 in the direction which is moving away from the plane. So as a result, this is because of the symmetry. So the electric field at that point and the electric field at that point should have the same magnitude, but they should have opposite directions. But what this thing is actually saying is that it doesn't matter which point you take. The point might be close to the plane or far away from the plane, doesn't matter. As long as the distance to the plane is much smaller than the size of the plane, the real size of the plane, the electric field has the same magnitude. So as a result, we will say that the electric field is uniform on the right side of the plane, meaning that the field itself, both in magnitude and direction, does not depend on position. In this region, basically, in this region too, the electric field is uniform. So E is uniform on the left side of the plane. But if you think about the whole space, the electric field is not uniform because it depends on position, because it changes direction when you cross this cross this surface charge density, cross this plane. All right, so there's one last thing in here. So there is a discontinuity of the electric field when you cross the plane. So when you are moving, let's say in here, if you are crossing the plane, you somehow suddenly see a discontinuous change in the electric field. How can you compute this? So that's basically the jump in the value of that function. So that's basically the electric field at the right minus the electric field at the left. Okay. So in any case, let me do the calculation in here. So on the right, the electric field has a positive component, and on the left, it has a negative component. And so therefore, the amount of the discontinuity is sigma over epsilon 0. So that's something that we have discussed before. For a finite disk, for an infinite plane too, we have a discontinuity in the electric field with the same magnitude. All right, let me stop here. In the next videos, I'm just going to play with these, since these kind of arrangements with infinite planes are used frequently, especially in the capacitor problems. Let's just look at solve some simple problems involving infinite planes.